Question 3, talking about two variable data. You can use your scatter plot in your calculator to get information if you don't have one drawn for you. This problem already has one drawn. All right, the scatter plot below shows the relationship between the lengths in inches at birth and heights in inches at age 18 for 10 randomly selected children. We want to describe the association between the length at birth and height at age 18. So the first thing you want to do is you want to recall what this means. D's for direction. Are we talking linear, non-linear, that kind of thing? Actually, directions, sorry, positive or negative. U, that's gonna talk about that's gonna talk about unusual points. Unusual points. We're talking about like outliers. Outliers being somewhere down there. Or are we talking about points that are way out here, or somewhere that's kind of out of the range of values we typically associate. F is form. That's going to be like linear, non-linear, that kind of thing. And then S stands for strength. How good is it? Positive. Is it strong? Is it weak? Moderately strong? That kind of thing. So think about that problem. Describe it. A quick couple sentences to describe this information. Pause the video, and then you can check the solutions here. All right. So for the Duffs, there's a strong. I would say it's strong because these values are pretty tight. Positive linear association between length of babies at birth and their heights at age 18. There seem to be no outliers. Now, let's recall what the least squares regression line is. Remember, it's the line that minimizes the sum of the squared residuals. So residual is how far a point is from the graph, and the purpose of a least squares regression line is to minimize the area of the sum of these squares in and around a line. So Duffs in context. Question 2. Use the computer output below to find the equation of the least squares regression line. Be sure to define any variables. From the computer output, that first number here, that constant, that's your intercept. That's your A value. And then that B value here is going to be your slope. So just keep that in mind. And remember, we do y hat equals A plus BX. So we put the intercept first, followed by the slope times the x variable, the input. We do use the S, we do use the R squared. We don't use all this stuff here yet, okay? So just focus on these 4 numbers. Make sure you interpret. So here's your equation. Your intercept is 19.7635, so 19.7635 plus 2.4532x. Y hat is your predicted height at 18, x is your length at birth, and these are both in inches. Okay, letter C, interpret the slope and y-intercept in context. It'll take a minute to do that. All right. So remember, the y hat is the slope or the predicted value here. So the slope B is at 2.4532. For each additional birth, we predict a person's height at age 18 to increase by 2.45 inches. Increase because that's a positive. So if that were a negative, we'd say decrease. And it's always the one by the x, and it's always by 1 unit. So for each additional inch at birth. So if I did 5 here, I would get an output. If I did 6, that output would be this much more than if I had plugged in 5. For the intercept, that's your starting value, right? So in this case, a baby born 0 inches long is predicted to be 19.76 inches tall at age 18. Of course, that doesn't really make any sense, right? So not everything is going to really have context to it, but that is how you interpret those in these settings. All right, letter D, interpret the coefficient of determination in context. Helps to have these numbers in front of us. All right, so coefficient of determination. That's r squared. R squared is 92.8. So let's move that over here. And let's see what's going on. We say r squared is 92.8. What does that mean? It means about 92.8% of the variation in the heights, variation in the heights at age 18. So that's the response variable. So about that percent of the variation in the response is explained by the lengths at birth, so the explanatory. So I encourage you to look up what that means again, but it's basically the percent of variation in the response can be explained by the explanatory variable. So it is a percentage, but it's directly related to the correlation, because if the r squared is 92.8, the r is going to be some either positive or negative sign of the square root of that decimal. We'll get more into that next. So first, let's interpret the standard deviation of the residuals. Well, that's this right here. That's 1.191. So we say on average, the observed heights at 18 are 1.191 inches from the least square regression line. So about how far off on average the observed heights are from the predicted heights. So difference, so we'd say basically typical difference between observed and predicted. That's all that really is. All right, correlation. Again, r squared is always given to in these. So r squared as a decimal is 0.928. So we're going to use that to get our correlation. So think about that. This is a positive, right? Your slope is positive. So if that were a negative, your correlation would also be negative. But since the slope is positive, we're going to keep that positive. So all we got to do is square root 0.0928 or 0.928, and we get 0.962. We're going to keep positive. Correlation is just a value. It helps you determine how strong a linear equation is. It doesn't tell you everything, but it helps determine strength. Doesn't tell you if it's linear or not, just helps determine how strong it is. Last one. Calculate and interpret the residual for a person who is 21 inches long at birth and 6 feet tall at 18. So residual is the observed minus predicted. So y minus y hat. So let's first look at the observed value at age 18. 21 inches long at birth and 6 feet tall at age 18. That's observed. 6 feet tall, 6 feet times 12 inches Well, you know that's going to be 72 inches. And since we're dealing with inches, we got to convert that, right? So that's observed. It's going to go there. So think about that residual, observed minus predicted. Try it out. Let's interpret. So we have 72 inches as the observed. Predicted, if we plug in 21 into the equation, we do get 71.2807 inches. So observed, 72. Predicted, less than that, 71.28. So you get a residual that's positive, right? What that means is on the least squares regression line, if your residual is positive, it's going to be above the line. That means the line doesn't under predicts the actual value. Okay, so your observed is positive if it's above, negative if it's below. Okay, so this is 72, 71.28. So we say a person who's 21 inches at birth is 0.72. You can round that to 0.72 inches taller than his or her predicted height. That's 71.28 inches. All right.